Okay, let's start. It's my great pleasure to introduce Christos. I think he probably doesn't need any introduction. He has been doing research in database and data mining and also some information in the field, and made a lot of contributions, and he's lots of awards. For example, database, he got the 2 best award from the ICDM and also the SIGKDD Innovations Research Award. And also his students together got so many best paper awards. And he's come from the country where the science comes from, right? Greece. So, and also, let's see, and also lots of good students, right? A lot of students get the presentation award and also become professor of Stanford. All right. Okay, we got anything? Let's thank you very much. Should I put a mic or something, or no? Okay. It's a pleasure to be here. I would like to thank Bing for the great hospitality and Tanya Berger-Wood for helping with arrangements, and Kitty also for handling 1 million emails for the trip, right? Also, I would like to acknowledge all the new friends, right? Isabel, Jacob, Liz, Clement, Philip, Uri, and Brian. And we'll start first. We'll see the why should we study large graphs. Then we'll see patterns in graphs, and then time-evolving graphs if there is time, and conclusions. Right? So why should we care about graphs? Because there are many graphs of vital interest. For example, the web, even a small portion of the web, which is publicly with very liberal NDA available from Yahoo, 1 billion nodes, 6 billion edges. How does it look like? Are there anomalies? Are there strange websites? And we won't go into the details, but these are scatter plots. Every dot is a website. The axes don't matter. What matters, and there is overplotting is indicated by different color, right? Blue means 1 dot. Red means a lot of dots at this position. What is interesting from these plots is that they don't have the expected shape, right? They're not Gaussians or mixtures of Gaussians. So if we squint very hard, we'll see a few dots here which are standing out by themselves, and they're worth investigating. Probably bad sites, probably scamming sites, or what, right? So web is one motivation. Facebook is another motivation, right? All the social network companies, Facebook, LinkedIn, right? Facebook claims 1 billion users recently. For those who care about money, Facebook has multiple tens of billions of dollars capitalization, right? And Google+, Yahoo networks, and so on, again, want to figure out are there groups, are there communities, are there fraudsters, how do people behave in the social network, right? Networks don't necessarily need to be networks between humans. So this is autonomous systems, UIC.edu, CMU.edu, they have a link. Every dot is an autonomous system. They have a link if they communicate, right? So in this graph of several thousand of autonomous systems, what is the most central node, which one we should guard against cyber attack, and so on. Nodes here are species, so this is prey-predator relationships, right? So this is algae, sardines eat algae, tuna eats algae, and tuna eats sardines, and so on and so forth. Want to figure out in this ecosystem, food web, want to figure out what is the species that if it goes extinct, the whole ecosystem will unravel. And the list continues. 10, 15 years ago, blogs was the rave, right? Everybody had a blog. Who points to whose blog, who is the most influential blog, who starts important news, and who has high influence, right? Computer security, who connects to my machine, does this person connect repeatedly, is this person or is this machine doing an attack on my machine, and so on. Again, for email, who sends mail to whom, who is the most central person. Recommendation systems, now there's a bipartite graph, people rate movies. A few years ago, there was the Netflix competition in the news, right, for $1 million to do better prediction of Netflix, right? So again, want to figure out in a bipartite graph, what is the best missing link. In general, for people with database background, every time we have a many-to-many relationships, this corresponds to a graph, right? So we'll see 2 problems. There are many very interesting problems in graphs. We'll focus on 2 of them for this case. The first is, are there patterns in graphs? And the second is on static graphs. And the second is, what patterns can we find for time-evolving graphs? And patterns go hand in hand with fraud detection. If somebody, forget about graphs for a moment, if somebody gives us these 5 points, if we are careless, we say, well, there's no pattern there, right? If we pay more attention, we say, no, these 4 points seem to be along a line, right? So we discovered the pattern. And when we find the pattern, we can spot and say whoever is not on the line, the few nodes that are not on the line are probably anomalies. So patterns and anomalies go hand in hand. So let's see the first part, patterns and fraud detection, anomaly detection. So the goal here is how can we find patterns in graphs? If we plot the autonomous systems like that, this is UIC.edu, CMU.edu, and so on, we don't see any pattern. In sociology, this is called affectionately known as the Death Star, right? It looks like a big blob. So are real graphs random? In which case, we should give up. The answer is no, right? We are all familiar with the 6 degrees of separation, the Milgram experiment, right? Some of us have wasted time with the Kevin Bacon oracle, which says if 2 actors play in the same movie, then they are 1 step away from each other, right? So how many steps away is your favorite actor from Kevin Bacon, right? And it turns out that almost every actor is 6 steps away from Kevin Bacon, and actually every actor is 6 steps away from every other actor, more or less, right? So small diameters is a pattern that real graphs exhibit while random graphs don't. We see that the in and out degree distributions have specific patterns, and we'll also see additional patterns. So let's look at the data. This was a 99 paper. So these are the autonomous systems, right? UIC.edu, MIT.edu, and so on, right? If we plot them according to the zip plot, which says find the degree of every node. So the vertical axis is a degree, the horizontal axis is the rank of this node according to degree. So rank 1 is AT&T.com, has the highest degree, 800, rank 1, and it goes here, right? Degree number, the IBM.com has degree 600, rank is 2, so it goes here, right? So if we plot 3,000 autonomous systems in logarithmic scales, they fit on a line. Despite the fact that they look messy, they obey this strange zip-like pattern. And actually, if it was a zip distribution, the slope would be 1. If it was, right now is minus 0.8, which is the generalized zip distribution. So why is this important? Because this breaks completely the standard assumption, right? That people would say, I tell you the degrees, right? The average degree is 3. What can you guess about the degree of everybody else? Well, the natural assumption is let's assume the ocean, so 3 plus or minus a little bit. Everybody should be between 2 and 4, right? That would be, if that was the case, then the zip plot we saw before should be looking like this dashed line, which is completely wrong, right? It's not even close to the reality, right? Okay, so we open a parenthesis here. So why is this, okay, so the Gaussian assumption does hold. So what is so important about it? The important about it from the computer science point of view is that it can help us design better algorithms or avoid designing disastrous algorithms. Here's an example. Suppose, consider the following very innocent looking query, right? We have a network. How many of you have a Facebook account? A lot of people, right? So one query is find out how many friends you have, that's easy. Find out how many friends of friends, how many people you have within 2 steps away from you, right? That's a reasonable query, let's ask it, right? So why not, right? So how long it will take, how many pairs, how many 2-step away pairs we would expect to see? Let's say that the average number of friends is 100, Dunbar's number, right? Sociology says people can keep track of 100 more friends and then they lose track, right? So in that case, we have 1 billion people at Facebook. Everybody has 100 friends. Each one of the friends should have 100 more, right? So 100 squared, right? Times 1 billion. If we do the math, this is 10 trillion pairs, 8 bytes per pair, right? So this should fit in a few disks, right? It should be a few terabytes, about 10 terabytes, right? So we would ask this query and allocate a few disks, right? And expect the answer soon, right? It turns out that this is not what is happening. What went wrong? The wrong assumption was that we did we made the Gaussian assumption, right? We assume that if the average is 100, everybody should have 100 friends, and they also should have 100 friends each. What is happening is that, yes, the average is indeed 100, but there are a few people who have huge degree. Justin Bieber has a million, yes, we're laughing, right? Tens of millions of followers. Actually, I understand that people at Twitter, they have a few servers dedicated just for Justin Bieber, and when it's his birthday, they are embracing for a tsunami of happy birthdays, right? So this is true, and it's not only Justin Bieber, there is also famous personalities, right? Barack Obama and so on, they will all have huge number of followers. So what will happen is, suppose that this is Justin Bieber at the center, and then 10 million followers. All of them have 10 million two-step away friends. So just Justin Bieber alone will generate 10 million square pairs, two-step away pairs, right? Which means if we do the math, this is roughly close to a petabyte. Instead of a few disks, we need a whole data center. This is the data center observatory at Carnegie Mellon. This is more or less half of this room. This takes as much space as half of this room, right? So we are way off. Instead of a few disks, we need a whole data center because we made the Gaussian assumption. If the average is 100 friends, everybody should have 100. No. Most of the people have one friend and they forgot their password like me. And there are a few crazy guys who have, right? There are a few people who have thousands or millions or tens of millions of friends. So then the conclusion is that if we're aware of such skewed distributions, either they're exactly zip or deviate slightly from zip, as we may see later. The idea is that we should be aware of the skewness and we should design algorithms accordingly. Sometimes we can exploit that, store Justin Bieber on a different machine and then do our nice algorithm on the remainder, right? And in general, be aware of this phenomenon. And continuing the parenthesis, when we have big data, backtrack, right? This is quadratic. This algorithm is quadratic on the highest degree, right? When we have big numbers, big data, quadratic algorithms are completely out of the question, right? So suppose we have an algorithm which is quadratic, like computer similarity matrix of some people, right? If we have 1,000 people, everything is good. If we have 1 billion people, then if the function we want to do takes, let's say, 1 second, then 1 billion square seconds is 31 billion years, 2 times the age of the universe, right? Which is completely prohibitive. We had friendly arguments with colleagues, said, well, we can use parallelism. Yes, if we use 1,000 machines, which is within the budget of a university, right? This makes the computation time 31 million years. This is the Oligocene period. We don't recognize these animals because we never saw them, right? It's 31 million years, right? Okay, suppose we have deep pockets like Google and Yahoo or a government, right? And we can afford 1 million machines. 31,000 years, right? Neanderthal time. Okay, suppose we go for broke, right? The GDP of the US is $12 trillion. So none of us for a whole year gets a salary and we spend all that money on machines. It will still take 3 years, the time it takes to graduate, roughly, right? So parallelism is not the solution for quadratic algorithms. So close the parenthesis, stepping down from the soapbox for a moment, right? And we continue with more patterns, right? So we saw that the degree distribution is not even close to Gaussian. It turns out that the eigenvalues of the adjacency matrix are also very skewed. Some of you may remember this definition. This is the definition of the eigenvalue of a matrix. This is a square matrix, 1,000 people, million people by million people, right? The connectivity. If you find a vector x for which this equation holds, the constant lambda is the eigenvalue, one of the eigenvalues. We can load our matrix to MATLAB, press the button and get how many you want, 100, top 100 eigenvalues, right? If we plot them, we see that in log-log scales, right, they still follow a skewed distribution, right? And this is interesting because we'll see later some algorithms based on that observation. So, pattern number 3, let's compute the number of triangles. Social networks, they have many more triangles than random vectors because if this is us and these are 2 of our friends, sooner or later we'll throw a party, we'll introduce them, and the triangle will close. So the question is, we are the blue node. We know that we have degree 3. How many triangles we are participating? In this toy example, the blue node participates in 2 triangles, right? So if you have twice as many friends as me in Facebook, how many more friends, how many more triangles, communities you will be participating? People will say, well, double the friends, double the triangles, right? What else? It turns out double the friends, roughly triple the triangles. Actually, the number of friends is n square root of n, or the number of triangles is n to the square root of n of the number of friends, right? So this is the opinions data set, who trusts whom. This is the degree, this is the number of triangles, this is some anonymous Smith who has a huge degree and a lot of triangles, and so on and so forth. And we see that a line of slope 1.6 fits well. And the same for an anonymized social network here, and for a Reuters data set, and so on. So now the question is, okay, how could we compute the number of triangles, right? For those with a database background, this would be a 3-way join, right? Select all my friends. For everybody, select all the friends of these people. Select the 2-step away friends. Make sure that these are 1-step away friends too. And this is it, right? It's 5 lines of SQL. But it will take forever, because what we are doing is we're finding the 2-step away friends, and Justin Bieber and Barack Obama will mess up the algorithm. It will fill up a whole data center with intermediate results. Can we do that faster, right? This is a quadratic algorithm, and we said we don't want quadratic algorithms. Can we do it faster? It turns out that in matrix algebra, this is a homework exercise. It's a 3-line proof to show that the sum of the cube of the eigenvalues, the ones we saw before, is the number of triangles. This is a theorem, right? No approximation or nothing. So this means this has two good news. One is that the eigenvalues can be computed in time proportional to the number of edges. So if there are 1 billion people at Facebook, they have 100 friends each, the number of edges is 100 billion, or 400, right? It's a relatively small number, it's not quadrillions, right? Moreover, because the eigenvalues are skewed, we can keep the top 10 eigenvalues. They are cubed, so whatever is the biggest eigenvalues, they will be cubed, and the rest of the eigenvalues won't matter anymore. They will introduce tiny error. So by computing the top 10 eigenvalues, we can have a good estimate of the number of triangles. It takes a little bit more of a matrix algebra manipulations to figure out the number of triangles for every person. Once we do that, then we can do this plot for every dot. This is Barack Obama. This is the Twitter. We ignore directionality. And Barack Obama has 10 million followers, degree 10 million, right? Using the cube of eigenvalues, we can quickly compute the number of triangles. It has a lot of triangles, right? Participating in a lot of triangles, 10 to the 8. Okay, that's good. We can do the same for everybody else. How would the plot look like? This is log-log again. Almost every plot we see will be in log-log scales. Would it be a line of slope 1, a line of slope 1.6, maybe not even a line at all? It turns out it's close to a line, right? With a lot of people, some of the people we can even recognize. This is Hillary Clinton back in 2008, when Sarah Palin was also running for president, presidential vice president, right? So this could be the end of this presentation, except that there is a cloud of points here which has relatively small degree. They wouldn't stand out if we check the degrees. The degrees are relatively 10,000 as opposed to 10 million, right? But they participate in a huge number of triangles. So what is happening with these nodes? Too many triangles means that probably they participate in cliques, right? So if we have a 5-click, this node has degree 4, right? But participates in a huge number of triangles, right? So this is what is happening. They're creating cliques. And closer look at the Twitter data, these are adult advertisers, Viagra and gray area situations like that. And they create probably sock puppets, like as Bingu has studied in other settings, right? They're sock puppets, they probably the same person, creating thousands of accounts, all of them point to each other so that all these accounts look trustworthy and important, so that they can scam people, right? Are there more patterns? Yes, this was part of the dissertation of Lemana Koklu. There are 10, 11 more patterns, and the more carefully we look at them, the more patterns we'll see. We presented the first 3 patterns here, but there are, we said, there are many more patterns. And we have a recent book which should be available for free from any library, electronic version at least, which has several more patterns. So, we talked about patterns. Let's see how we can use patterns to find anomalies and strange nodes. Because as we said, patterns go hand in hand with anomalies. So, this is a paper by Alex Butel, who is a PhD candidate at Carnegie Mellon. So the goal is, we know he spent time at Facebook, so he had the data of accounts who give likes, a thumbs up to a given page, right? So now, and also the timestamp. So the question is, figure out which of these likes are paid, which of these likes are not really, are false, right? So here is the drawing. We have all these people here, right? We have all these pages. This is a beer. This is the Black Spy from Mad Magazine. If you remember it, you are more than 40 years old, right? Batman and other things, right? The line means, the color of the line is the date. So green is the beginning of the month, red is the end of the month, and so on. So given that, can we say that there is some weird behavior? Let's make the problem even more clear. So let's see the adjacency matrix. Here are all the people, right? Smith, Johnson, Thompson, right? Here are all the pages, Mad Magazine, beer, and whatever, right? A dot means that this person liked this product, gave a thumb up to this product, right? And the color is, denotes the day of the month. Red is the beginning of the month, purple is the end of the month, yellow is the middle of the month, and so on, right? So what we would like to do is to rearrange the users, rearrange the products, so that if there are blocks of users and blocks of products with similar behavior, they are suspicious. So if all these people like this product, beer or whatever, more or less the same time of the month, see, this is the all blue, right? Like the Mad Magazine, right? The Black Spy, during the same time of the month, green, right? This is suspicious, this is not organic. These are people who are working in lockstep, probably because they are robots, probably because they are scripts that some clever guy wrote them, and for an amount of money, this person makes all these accounts give a thumbs up to the products that pay him or her. So the question is, how do we spot this type of lockstep behavior? I see people photographing, the things are on the web, so, but you are welcome, of course, to photograph. Right. So this is the goal. Rearrange the matrix so that we find groups of people, groups of products which have this similar temporal behavior. How would we do that? There are many ways. The one that was done in the paper that was published, approved by Facebook and published eventually, is something that looks like belief propagation. Pick one product at random and blame it. Consider that it's a bad product for a moment. Whoever liked this product gets part of the blame, right? Now, actually, it's a little bit more complicated. Figure out at what point of time there were most of the people, the vast majority of the traffic for this product. Let's say Tuesday, okay? Tuesday is red, so everybody who said thumbs up on Tuesday for this product is blamed, right? And then we continue. So these are probably bad guys. Let's see what else did they like. They liked not only the Mad Magazine person, they also liked the beer, they also liked the Batman, right? Okay, so these are suspicious products now. Do the same. Figure out what was the peak time for Batman, figure out what was the peak time for beer, who gave thumbs up during these suspicious times, blame this person back. Now you see that this person got exonerated, right? Was not blamed the second time. So after a few blame propagation back and forth, if the groups stabilize, then probably they are both suspicious, right? The group on the left and the group on the right, the group of products on the right, are both suspicious, right? If it does not stabilize, means we started from an honest product and the algorithm didn't reveal anything. It shouldn't reveal anything, right? So this algorithm, we are skipping a lot of details. There was a very complicated implementation on MapReduce at Facebook, But the bottom line is that it has been used. This is the number of people blocked by this product. The vertical axis is eliminated for obvious reasons, right? Facebook does not want to give out trade secrets, right? And we see that the number of people caught is decreasing. One explanation is probably because the bad people gave up. They are not making money anymore, so there's no point in even trying. That's the explanation. What is also interesting is that among the people who were blamed and actually verified by phone calls, right, from Facebook employees, the vast majority of them were hijacked accounts. All these were hijacked accounts, only 23% was fake accounts, right? Which is very interesting to know because hijacked accounts are extremely difficult to detect, right? They have more or less normal behavior, except for 12 midnight that the cron job wakes up and starts doing weird things, and then they look normal again, and so on. So this is something interesting to know. Let's see other ways of spotting fraudsters. So this is the F-box method. So the idea is the following. Usually when we see bipartite cores, these are suspicious. All these people got money and give thumbs up or thumbs down to all these products, right? Normal people don't work in unison like that, right? You like a few products, I like a few others. There might be a small intersection between the things we like or we don't like, right? But we never have 50 people liking exactly the same 20 products, right? And also clicks are also suspicious. As we saw, it's probably sock puppets, right? So the question is, how can we spot them? The idea, the high-level idea is that for every node, we can plot the out degree of this node. Every dot here has two attributes: the out degree, the actual out degree, and the vertical axis, the out degree. After we do some summarization of the graph, some singular value decomposition. We won't describe the details, but if a node is well described by our model, this graph should be here. This node should be here, right? Everybody below this line, this is logarithmic scales, everybody below this line is not well reconstructed, so probably something is happening, right? Looking at this graph, we see that the vast majority of nodes are here. This is heat map, right? So there are thousands of nodes here, tens of nodes here, one node every blue dot, right? So the majority seems to be behaving like that. So assuming that majority is normal, these are all probably okay nodes, right? What is stunning is that at 10 to the minus 25, right, this is the exponent, and a very suspicious horizontal line, right, we have a lot of people who are not well reconstructed at all. This person has degree, this dot has degree 400, and the reconstructed degree is practically 0, right? So our summary, our SVD summary, completely missed this person. Let's look at this person more carefully. It turns out that a lot of these people they're not even trying to hide, right? So this is this account, and this account, Lekan or Lawove, whatever, says sign up free and get 400 followers, right? So clearly this is not an honest person, right? It will give free followers to people, right? The second account is exactly the same again, similar name, right? Similar message. So these are suspicious accounts, which are spotted by the spectral decomposition. Let's see another method which is similar to the previous two methods, to copycats and the spectral method. This is belief propagation. So this is joint work with Polo Chow, who is now professor at Georgia Tech, and Shashank Pandit, who is in Silicon Valley, Facebook. So this is eBay. Every node is a seller or a buyer. And edge means that this person sold or bought something from this person, and it was a happy transaction, right? Feedbacks, eBay has feedbacks. Almost all feedbacks, 99% of the feedbacks are positive feedbacks, because negative feedback is declaration of war and the other person retaliates and it's nasty, right? So this is the situation. We are at this point of time, we want to buy a laptop, an expensive laptop. This person is advertising an expensive laptop, is willing to sell, and we see that this person has 1, 2, 3, 4, 5 positive feedbacks. Looks honest, right? How about this person? Same laptop, he or she is willing to sell us a laptop for the same price, 2 positive feedbacks. Which one is most trustworthy? 5 versus 2, if we stay on the count, the top one is most trustworthy, right? But if we look at the structure, this is a bipartite core, right? Which, as we said, is suspicious. It turns out that not only suspicious, they are fraudulent. What is happening among the many types of fraud, there is the non-delivery fraud, which exactly says, I'll sell you the $3,000 laptop, give me the money, and I never send you the laptop. And why are you duped? Because you believe that this person, since this person has 5 positive feedbacks, is a trustworthy person. How are they doing that? Probably these are sock puppets. The same person logs in as yellow, accomplice, logs in as red person. The red and yellow is from our algorithm, right? It doesn't show on eBay, right, of course. And then the yellow, the accomplices, are accounts who have been in eBay for a long time. They have happy transactions, successful transactions with honest people. Green is for honest, right? They buy small price items because eBay gets 10% of whatever is the transaction cost, right? So therefore they have good reputation. They have never done anything bad, the yellow guys. Except that they give very strong positive feedback to the red accounts, which are new accounts created 1 or 2 weeks ago, right? And the accomplices make the red guys look trustworthy. The red guys don't deliver, they get the money, or they get your money, they don't deliver the laptop, of course you complain, eBay shuts down the account, so this guy goes away, right? This note goes away, but this guy logs in again as Smith123, Smith124, Smith120, right? Logs in again, his friends, probably himself, they all give positive feedback to the new account, and the machine gun is ready to fire again. It's a very clever trick. If we look at the compatibility matrix, what is happening here is that honest people interact with honest people or with accomplices. Very rarely they interact with the fraudsters, one in a million, right? And they lose their money. Accomplices interact with honest people, and at least they claim they interact with fraudsters, right? For a small fee of a fictitious product that they don't really sell, right? And fraudsters interact with accomplices and also with, that's it, interact with accomplices. They don't interact with each other, right? Because every interaction costs 10% of whatever was the sale value, right? And therefore, there's no point, right? They already have good reputation thanks to the accomplices. It turns out that with belief propagation, if we have this compatibility matrix, we can run the belief propagation algorithm, and this algorithm automatically labels nodes as green, yellow, and red with good accuracy. Sometimes it flips the red and the yellow, but most of the time it's very accurate. And we did experiments, and the accounts we found as suspicious, a week later they were shut down by eBay. A lot of them were shut down by eBay. Let's continue. So let's see how belief propagation can help. It can help in many other settings. So this is the Polonium system, also by Polo Chow and colleagues at Symantec. So the problem there was, again, a bipartite graph. So Symantec keeps anonymous information about all the machines. If I have installed Symantec product, right? So they know my machine, and they get hash codes for all the files that they scan. So this is Microsoft Excel, this is Microsoft Word, this is Microsoft Excel, or whatever, right? And the same, this is your machine, some other files, and so on and so forth, right? A huge number of machines, millions of machines, and millions of executable files, right? And the question is that doing static analysis, they figure out, Symantec figures out that this is an infected copy of Microsoft Word, this is a clean copy of Excel, this is a clean copy of Microsoft Word, and so on and so forth. For a few of them, they have clean or non-clean. For the vast majority, they don't know, right? So, how can we exploit the machine information to fill in the gray nodes, right? And this is completely disproportional. The gray nodes is the vast majority, millions of them are unknown, and a few of them are labeled, right? The idea is to use homophily. this is an infected file, this belongs to a machine. Apparently the sysadmin of this machine is not very careful, either didn't install the software correctly or doesn't pay attention or whatever. Therefore, every other file that is on this machine is suspicious, right? On the other hand, this machine has an honest file, another honest file, so probably this has a careful sysadmin, so everything else is probably, with high probability, is a clean file, right? So this is the idea, guilt by association, right? And this is exactly what belief propagation is based on. If I'm honest, my friends are honest, their friends are probably honest, and from then on we lose track, right? So how to do that quickly on a graph that has 37 billion edges? It turns out that the belief propagation algorithm is linear on the number of edges. We pass messages left and right, and eventually it works. It scales up, it can be parallelized, this is done on a Hadoop system. It can be parallelized, and it gives, using the neighborhood information, using the guilt by association, the curve is very close to the ideal curve, right? The point is very close to the ideal point. And what is important in real-life application is to have very small false positive rate. False positive rate means how many honest people would blame, right? We want this to be tiny because we have, Symantec has millions of installations, even 1% of them, and this is 100,000 people we want to blame. We don't want to anger our customers, right? So false positive rate is very important, and this algorithm reduces the false positive rate exactly because it takes information not only from the static analysis, but also from the neighborhood, from what the machine also, other things that it contains. Let's see more details about belief propagation and financial fraud. So this was exactly the same algorithm, belief propagation, for an accounting application. So this is the marketing account, this is a cash account, this is the sales account, this is something else. So in this accounting firm, that was PricewaterhouseCoopers, in this accounting firm, there is also static analysis. And say, if an account has a lot of round numbers, 1,000 check, 1 million check, and so on, this is sort of suspicious. Real amounts are probably 1599 and things like that, right? If an account has a lot of owners and the owners are all in the same address, this is also suspicious, right? Why are they living in the same house? So there is a little bit of blame on these accounts. The rest of the accounts seem honest according to this static analysis, right? Can we figure out what is the most suspicious account? The idea here is, again, belief propagation. If this account is slightly suspicious and there is transfer of money from this account to this account, maybe this account should be suspicious too, right? The most striking situation is in this setting where this account has 3 semi-suspicious accounts, therefore this account is blamed a lot, right? Why does this account have so many suspicious friends, so many suspicious transfers, right? And that's what belief propagation is doing, is collect evidence from the neighbors, and after we pass messages back and forth, right? We pass messages, we pass them back, and so on and so forth. After the algorithm stabilizes, this account which has 3 semi-suspicious neighbors and is reasonably close to a suspicious neighbor, this is the one that is blamed most. So if you are an auditor, this is probably the account we should start investigating. And because accountants also have limited time and they have to do the audit as quickly as they can, right? So this also gave good performance versus static analysis, which does not look at the neighborhood. This is the area under the curve. This is false positive, true positive rate. Higher is better, and taking neighborhood effects into account, the curve goes higher. And right. Let's see more details about belief propagation. So belief propagation looks very much like PageRank, right? If I'm guilty, probably my friends are sort of guilty, their friends are quasi-guilty, right? PageRank says the same, right? So if I'm important, my friends are sort of important, their friends are quasi-important, and so on, right? Are there correlations? It turns out there are. Let's see the definition, the problem definition. We have a social network, right? Or any type of network, right? We know that these people are of type green, let's say honest. We know that these are of type red, dishonest, or whatever, right? Smokers or non-smokers or whatever, right? And for the vast majority of the nodes, we don't know anything. So what can we guess? about node number 26 or node number 3, right? We as domain experts, we have to make some assumption, right? This compatibility matrix says homophily. If there is a green person, his or her friend should be green, okay? Red people should associate with red people. Homophily is not the only possible compatibility matrix, right? We could have heterophily. Silent people prefer to have talkative friends, and the other way around, because if two silent guys get together, nobody talks, and it's not a pleasant meeting, right? And it doesn't have to be 2 by 2, it could be 2 by 3. We saw honest, accomplices, and fraudsters in the case of eBay before, right? So we could have any type of compatibility matrix. Let's stay with 2 by 2 compatibility matrices, and let's revisit the question. Belief propagation says, if I'm good, my friends are good, right? Or if I'm silent, my friends are talkative, and so on. This is similar to the random walk with restarts. If I'm important, my friends should be important, their friends probably are important too, and so on. Semi-supervised learning, for those of you with a machine learning background, more or less says the same thing, right? So, they seem related. Are they related? It turns out that they are not identical, but extremely similar. We don't expect you to remember these equations, right? But this is the identity matrix, 1 million people by 1 million people, right? This is the adjacency matrix, who is friends with whom, right? The adjacency matrix here. This is the diagonal matrix, which has the degree of this guy is 1, the degree of this guy is 2, the degree of this guy is 1 again, so this is the diagonal matrix. This is exactly the equation for random walk with restarts, right? Or personalized random walk. If these are your favorite sites, the y vector tells you which site do you want. I don't want site number 1, I do want site number 2, UIC. I do want number 3, CMU, right? Tell me which other site should I visit, are probably of interest to me, right? The vector x will give exactly the sites that are related to, what did we say here, UIC and CMU, right? And this is exactly the equation for random walk with restarts. This is the equation for, the approximate equation for belief propagation. Notice that we have the identity matrix, we have the diagonal matrix, but not exactly in the same form. We have the adjacency matrix with a negative sign, okay, makes sense. And again, in all cases, all 3 cases, we invert a matrix which depends on the adjacency matrix, which eventually says, look at the neighbors, get some information, look at the 2-step away neighbors, water down their information, the 3-step away neighbors, water it down even further, and this is your guess for whatever should be the label for me, right? Green or red, right? So the methods are similar. We're skipping a lot of details here, right? The method can be implemented. It's a matrix vector multiplication, can be implemented in any setting, including Hadoop, and with a Hadoop implementation, it is much faster than it scales up linearly with a number of machines, and also linearly with a number of non-zeros. The horizontal axis is the size of the graph, the number of edges in the graph. And it also is better, faster than the standard belief propagation, because for subtle issues there are some less intermediate results. Right? Lower is better in this case. Right? So this is the summary of part 1, and probably we'll have to go quickly. There are many patterns in real graphs. Real graphs are not even close to random, right? Small diameters, power laws in everything we can imagine, degree distribution, eigenvalues, and so on. We should be very careful about the Gaussian trap. The average, in these settings, the average is much, much different than the maximum. In Gaussian distribution, the average, the maximum, and the mode are close, right? Here, they are far, far away, right? And there are a lot of tools for anomaly detection and fraud detection. Lockstep tools like copycats, spectral methods like FBox, and so on. And the message is that patterns and anomalies go hand in hand. Questions before we move to number 2?
Okay. I have a question. So this power law distribution, if it's a Gaussian distribution or it's a power law distribution, would this belief propagation behave slightly differently?
Very good question. So the belief propagation will, this is true no matter what the matrix is, right? So it will give the correct, the standard results, right? But you're right. If this adjacent matrix is full of ones, so this is Justin Bieber and has 1 million followers, then we can think about faster algorithms to handle it. We can do some partitioning, some careful partitioning, right? But even if we don't do anything, this is proportional to the number of non-zeros, right? Very good question. Thanks. Anything else? Yes.
If a malicious party is aware of the algorithms used here, could they easily just circumvent detection?
Very good question. So some of these algorithms require knowledge of the whole matrix, which the fraudster won't know, right? Facebook knows who is friends with whom, but the Smith person who is a fraudster will only know his friends, right? So Facebook has an advantage over the fraudsters. Probably fraudsters won't even do that much, right? The dumb fraudsters will give up. If they cannot make money, they will give up. The smart fraudsters will keep on doing smarter and smarter things, right? Actually, one action that fraudsters are doing is they play with thresholds. They say, okay, the customer paid me to create 1,000 followers. Okay, so I'll give 100 followers from my botnet and another 100 followers from another botnet, right? If I'm caught, then I give 50 followers from one botnet, 50 from another, right? I start playing with the numbers until I'm not caught, right? And it's a cat and mouse game, right? Very good question. Yeah, it's hard. My guess is that super smart fraudsters will eventually make it. The same way super good burglars will break into anything, right? But if there's no benefit, they won't.
Really smart ones work in banks.
Let's not go there. Yeah. Right. Good. Okay. Other questions? Yes.
So you believe propagation, how is compatibility methods? Are they learned or are they self-correcting?
Very good question. It's given by the domain expert. The compatibility matrix, right, is given by the domain expert. Here we assume homophily, and 90% of the times it's homophily, right? Because this is usually a bird of a feather flock together, right? This is very rare. This was astonishing, right? This was due to super smart criminals who created this amazing scheme with accomplices and fraudsters, right? Yeah, but it has to be given. Some colleagues are trying to learn the compatibility matrix from the data, but usually in these settings, we have so few labeled data, right? Say, how often do we see a green guy with a red guy? Well, never. How often do we see a red guy with a red guy? Never, right?
Yeah.
So it's hard to learn it the traditional way.
Yeah, I actually really feel a paper. All of them say they will do that in the future.
They will do that in the future, yeah. Thanks, yes, we'll do that in the future too, yeah. Right. Any other questions?
So
Yes.
what about approaches where sort of link farms and other things are used to propagate these likes? That is, it's not just like one person or one bot,
Yes.
but a farm of such things, a data center of.
You're absolutely right, and this is where if the farms are not super smart, they will have this type of behavior. They will have lockstep behavior, right? So all these people from the farm will satisfy all these customers, right? If we rearrange the matrix in a clever way, through SPD, through grouping, through propagation back and forth, maybe we'll see that, hey, this block shouldn't be there, it's too rare, right? These blocks don't happen, right? And then we can spot them, and Facebook can ignore the likes or shut down the accounts or something. So link farms, if they're not smart, they will have this behavior and they can be spotted. Good question, yeah. Yes.
Yeah, is it fair to say that social networks and networks in general are highly structured objects, and if you want to fake them, you really essentially have to create another one like it?
Correct, yes. And blocks like that are not natural. Or at least, yeah, why would 50 people click the like button on 60 products? Exactly the same 60 products, right? Yes, that's exactly right. So the question is, how do real graphs look like so that we can spot deviations from normality, from organic behavior, right? Other questions? Okay, let's. There's not much time, but let's see how much we can cover from time evolving graphs. what can we say about time-evolving graphs? Right? So here, so far we talked about static graphs. Smith called Johnson. Suppose we're hacked by AT&T or some telephone company, right? Smith called Johnson, we put a dot. Smith called Thompson, we put another dot, right? So this is what happened today. So this is all the phone calls today, right? Next day, Tuesday, some other phone calls happen. Wednesday, some other phone calls happen, right? Now we have source, destination, and time. Can we find patterns and anomalies there? And how should we proceed? And it turns out that this is obviously a generalization of matrices, right? Matrices have 2 axes, this has 3. The official name is modes, right? And this construct is called a tensor, right? We can call it data cube, but the mathematical name is tensor. And they don't have to be users, humans, right? This could be authors, this could be keywords, this could be data, right? So Smith publishes a paper on support vector machines, 2014, right? So we get all these dots, right? And then we want to find communities and figure out which people work on which areas and how this changes over the years, right? 2014, 2015, and so on, right? This can continue. It could be, none of the things could be humans. And the third axis does not need to be time. This is people who work on semantic networks or web text mining, right? They have triplets. So actually this is inspired from the NEL project headed by Tom Mitchell at Carnegie Mellon, where they scan websites. For every website they do named entity extraction, and they say we have triplets. The facts are triplets. Obama is president. The verb object is the US, right? So we put a dot in the appropriate place. And again, we want to find communities, we want to find the politicians, the artists, and so on and so forth. In general, we may have 3 modes, or even more modes, 4 or 5 or 6 modes, right? So the second problem we want to handle is coupled matrix tensor factorization, right? So suppose we have subject, verb, object triplets, and for some of the subjects we have additional information. So for the subject hammer, we put a person in an fMRI machine, and we see that these parts of the brain get activated when people hear the word hammer. The other parts of the brain activated when they hear the word something else, or the word honeybee, right? So now the question is, can we have a 4-way correlation? Which voxels get activated for what nouns, for what verbs, and what objects? So let's see the first part. Here is a quick one slide description of the singular value decomposition. We have a matrix like Netflix, people who like products, or grocery store, right? So these people buy these products. Suppose that there is a perfect, beautiful green block here. All these people buy all these products. All these people buy all these blue products, and all these people buy all these pink products, right? See, this is the perfect, the textbook case for singular value decomposition. If we load this matrix on MATLAB and press the button and ask for 3 hidden variables, it will say the first hidden variable has the U1 vector, this is the participation vector. The first user participates here, the second user, so here are all the people who like meat products, suppose that this is steak and chicken and so on, right? The second hidden variable will give you all the people who like, vegetarian products, and here are the vegetarian products, right? And here are the children who like cookies and stuff, right? So if we have blocks, the SPD will find these blocks perfectly. And coming back to your question, if this is a matrix of machines visiting machines, or users visiting likes, the blocks will be beautifully, and the blocks are beautifully clean like that, right? They will be spotted with the first few singular values, right? Okay, close parenthesis, this was SPD. What happens if we have tensors? Suppose we have beautiful 3-mode blocks. All these subjects, these are all, let's say, politicians, Obama, Merkel, Cameron, and so on. These are objects, US, Germany, England, right? These are verbs, president, chancellor, and so on, right? If we have a beautiful green block like that, Then the tensor analysis, the so-called parafact tensor analysis, again, we don't need to know the details, so we have to do load it in MATLAB, download the parafact toolbox and press the button. We'll get a triplet of vectors which will give us the participation. So all these people, Obama, Merkel, and so on, participate in this concept. As humans, we say, hey, these are politicians, right? All these vectors will have high values for the countries, US, Germany, and so on. And all the entries here will have high values for leadership vectors, right? Chancellor, president, and so on. If there is another beautiful block, completely disassociated from the green block, let's say the artist will have Eric Clapton plays the guitar and Lady Gaga sings and so on. The new vector, the new triplet, the third triplet probably will correspond to another concept, let's say athletes, right? So Roethlisberger plays with the Steelers and so on. So this is what the parafact does. Right. So we applied this. We had an anonymized data set from a small European country, 4 million people, right? Caller, callee, and time 15 days. If we do parafact, we get latent variables. So one of them was not very interesting, right? The time was sinusoidal over a week. Okay, fine. But the second or third vector, I forget, the second or third the set of triplets was very, very interesting. There was one caller, here is 4 million, right? Let me go to the next one. In one of the triplets, in one of these latent variables, there was only one caller, nobody else talked. There were 5 recipients, more or less the same amplitude, right? And so this person called these 5 people for about 3 days and then stopped. The whole thing stopped. There was another triplet where there was one person called another person roughly 2,000 times within 3 days, and that's it, never again, despite it was a whole 15-day interval, right? Unfortunately, things were anonymized, and we were thankful we had the data set at all, let alone, and so we couldn't trace it further. But tensor analysis can spot interesting settings like that. I think we're running out of time, yes. So we'll skip, yes, we also applied on brains. We're discussing with Philip about brains. We can do the same thing. We can look for latent variables for brain analysis, and if we show words to people, if we show words and ask them questions, so we saw the word glass, the word tomato, can you pick it up, can you hold it? The tensor analysis, which we didn't elaborate, will group together words, will group together questions, and will group together brain scans into latent variables. The most interesting latent variable is group number 3, which says that glass, tomato, and bell belong to the same group. Can you pick it up? Can you hold it? Is it smaller than a golf ball? Belong to the second group. And the brain scans have high activity in the premotor cortex, which in retrospect makes sense. These are all small items. They all fit in our hand, and apparently when this question comes up, the human brain of the subject says, oh yeah, I could hold it, so even the thought of holding something creates activity on the motor cortex, which is responsible for doing motions, right? So this is work we are doing with Evangelos Papalexakis and colleagues. Let's keep that. And we are at the end of the presentation. These are the sponsors. We are grateful for their support. These are the people who worked on this project. And the conclusions are that big data are valuable. They can help us find patterns, and patterns go hand in hand with anomalies, right? We cannot find anomalies if we have no expectations of what is normal or useful or typical, right? Large data sets can help us find things that would be invisible otherwise. Remember the case of the adult advertisers here. If we look at degrees, 10,000 degrees, normal, right? A lot of people have degree 10,000, right? A lot of people have, several people have 10 to the 8 triangles, right? But the combination is rare and suspicious. And if we were to do sampling, we may have missed those few thousand advertisers. The second is that Tensors is a powerful tool to analyze multi-mode matrices, right? And here are the citations. And the take-home message is that cross-disciplinarity is valuable. In order to do this analysis, we We used the M45, one of the biggest, back then, 2008, was one of the biggest top 500 supercomputers, and Yahoo allowed us access. Hadoop was necessary to do the analysis. Matrix algebra was necessary to do the sum of the cube of eigenvalues, because otherwise the triangles would be out of the question, right? Here, for the brain scans, we needed tensor analysis, we needed medical experts, and so collaboration is important. And that's the end of the presentation. 1 minute overview. Thank you. Questions? Yes.
Where can I take the online? Where can I find
Slides.
The slides are on my website, so if you go under talks, it will be under 15 UIC. But I'll broadcast it, yes.
This parafax stuff sounds really fascinating. Do you use it to run it?
No. Yes and no. If the tensor is sparse and small, reasonably small, up to 1,000 by 1,000 by 1,000, right? It can run on a desktop. And this is open software from Sandia Labs, from Tamara Kolda. And you can use it. The gigatensor that we mentioned, the gigatensor that we didn't mention, but it's on the voice, runs on top of Hadoop. And Hadoop can run on emulation mode on a single machine. Yeah, thanks.
To extend it, actually we're doing a implementation of sparse matrix, vector matrix multiplication on GPUs. Speeding up. On GPUs. Speeding up.
On GPUs. Yeah, sure. That's also the trend, yes. GPUs, yes. Very good. There was another question, yes.
There's a new graph computing paradigm called multi-centric, such as Google Pressure and GraphLab from SAMU. And my question is, which graph applications are fit for a Hadoop-based paradigm and which are fit for the multi-centric paradigm?
Very good question. So they are all node-centric, right? Either they have the think like a node, right? Or which means send messages over the edges. I'm a node, I collect information from my neighbors, right? And then I ship back information to my neighbors. This is also a matrix vector multiplication in algebra, right? Matrix algebra. And it's exactly the same as a join in a database. So the three things are exactly the same. Think as a node. Matrix vector multiplication and joins are the same thing. Which one is the best? It depends on how large is your data set. If it fits in memory, MATLAB. If it needs to span multiple memory of multiple machines, then GraphLab is good, and Giraffe, and so on. And Pregel is not available, but Giraffe, right? If it has to spill to the disk, then gigatensor that we didn't mention, and so on. Because these methods don't spill to the disk, right? GraphLab spills only one disk, right? GraphC, but not more than one. It's possible to make it, but it will take time, right? And there's also GraphX from Joy Gonzalez, built on top of Spark, also spills to the disk. So it depends on the short answer is depends on the size of your graph. Which one is most suitable? Good question. Yeah.
So tensors are great for multidimensional matrices and multimodal matrices when one of the unless one of the dimensions is really time. Because what's different about time versus everything else, every other kind of mode, is that there is order, and order is important. So you can't rearrange, you can't cluster in time really by rearranging different times arbitrarily. So
very good question. The quick and dirty answer is let's ignore this fact. and the tensors. Oops, sorry. And the tensors will.
It's okay.
and the tensors will still find interesting things. The other thing we can do is what we have done with Jimmy and Sun is for time we do wavelet analysis. So for every fiber, you do the wavelet coefficients. We decide to keep the top 100 biggest coefficients, the same 100 for everybody. And then they're sort of decorrelated. Wavelet, and then we go on to the question, okay, Haar wavelets, Dobeschi wavelets, what if there is a weakly periodicity, why not take, wavelets are powers of 2, right? And 7 is not the power of 2. So the idea is that we could do some pre-processing on the time series, let's say, average, or daily average, weekly average, difference of first day from second day, and things like that, so that they're sort of decorrelated. very good question.
Still working.
Yeah. Right, yes.
In tensor factorization here, is it necessary that the input should be properly clustered? I mean, it's
No, a very good question. No. Because if this is a nice, beautiful block here, the first few lines will be high, everything else will be zero. If these lines are randomized, right, but still it's a block, if you reorder them back, it's still a block, then the tensor will say that now that you randomize things, line number 3, line number 20, line number 3000 belong to the first concept, belong to the politicians, right? And then you can pick and choose and say, these are the politicians. So you don't need to sort. The parafag will tell you how to resort things back if you need to sort them.
So we can provide a random matrix.
Correct. Correct. Very good question. Correct. Yes.
To follow up, what if the blocks overlap?
Then things will get. Then it will happen even worse things that when SVD has overlapping blocks. In that case, then we have to go for heavy artillery like ICA, independent component analysis, which we can discuss offline. Right. Yeah. If they overlap, it won't be as pretty. Or if there are some nodes, some noise here, some noise there, things won't be as beautiful and nicely coordinated. ICA will try to do a good job. Tensor ICA, I think it exists, but I haven't used it, so I don't know. But yeah, that's also a good question. Yes?
Any questions? No? Okay, that's thanks.
None.
Thanks.